Let's have a look at the second order differential equation question in the paper you did. It's one of the hardest topics, but therefore it's the same every single time you do it. And therefore I think there's real easy points here if you can learn this. Now this question guided you through it in a rather unhelpful way, but you should be able to do this entirely without guidance. So you've got a differential equation here deriving from this. Let's try and understand it first. This x here is a distance that this point is below this dotted line. So because it's a spring, assuming this is heavy, it'll fall down. So x will get bigger, but then it will spring back, and x may even become negative. Then it'll fall, and it'll bounce up and down. So the distance x is changing. Really, it's a displacement, so that it can be positive and negative. Its speed is changing. At some points its speed will be 0. When it reaches the very bottom, it'll stop and then it'll spring back. It'll have positive and negative speed, which is dx by dt, and therefore the acceleration is involved. And all of this information can be captured in a single equation. This is the acceleration of this point. This is the speed of the point, and this is the position of the point. Remember, displacement is best understood as position. So all of that information is captured in a single equation. So that's what's going on, and you should know how to solve this. And the way you the fundamental method is you convert it into a system of differential equations, otherwise known as a coupled differential equation. And the method is we substitute y for dx by dt. So the second you see a second order differential equation, there's nothing else to do other than to substitute this dx by dt for y. We differentiate this straight away. We always do it. We just differentiate this. Dy by dt equals the differential of that. In other words, the second derivative. And now I'm going to substitute both of these things into here. I simply rewrite this as this. So this is the same equation. This equation here is exactly the same as that one. And remember, the purpose is I'm trying to turn this equation into a coupled system. So, and I have it. Here's dx by dt. Here's dy by dt. I just write them out. So I'm going to write these out now paired together. Now notice I've done it in a super careful way. Dx by dt is equal to y, and dy by dt is equal to this rearranged. But I've done it super carefully. I want it to look like a standard question. So the dx by dt is at the top and the dy by dt is at the bottom, and then x and y are in order. It's really important I set it up like this. This is why I've got this blank here. I've got no x's and one y. Okay, so now you should know the method. This is now a very standard question. A coupled differential equation is, I think, fundamentally quite an easy one, and it's to do with eigenvectors and eigenvalues and all that. And we simply not simply, but we turn this into a matrix equation, just extracting the coefficients here. You should understand this. Why are these two things the same? Well, let's multiply this matrix out. Read across the left one down the right one. No x's, one y. There it is. Then read across minus bx's and minus ay's. There it is. Remember, this is x speed, the speed that the ball is going in the x direction. Y, remember, isn't really a y coordinate. It's a substitution. But nevertheless, I can now easily do the question. And so they told us A and B were 18 and 77. And so we do eigenvalues and eigenvectors. You should know how to do that. You should be able to rattle that off. And we got, I think they told us the eigenvalues were -7 and -11, and you just had to use the method to find the eigenvectors. Some people made errors here, and it's such a shame. So here's the eigenvalues and eigenvectors paired up, always pairing them up. It's an absolute coincidence that the eigenvector looks like the eigenvalue. That's not a thing. So it's slightly odd, this, but it's no problem, but you shouldn't expect that to happen. So then on the formula book, it simply tells you what the solution is. This is called the solution of a differential equation. On the formula book, it writes this left-hand side as a sort of bold, strange X. You mustn't write it like that. Write it like this. Remember that a solution of a differential equation is a coordinate. The differential equation is telling us how the sort of flow is, what direction it's going in for any given coordinate. So at the coordinate 5, 2, we could work out what its x direction and y direction is from this. But this simply by saying, well, after 6 seconds, I am at this coordinate. After 1 second, I'm at this coordinate. And so we need to find A and B, and they will always tell you a bit of information. It will always be at the start, because when t is equal to 0, it makes this so much easier. And it said it's x is equal to 5, and it said dx by dt is equal to 2. What is dx by dt? Well, remember the whole thing right at the start was that y is equal to that in this type of question. In other coupled differential equations, it's just a coordinate. So we simply put x equals 5, y equals 2, when t equals 0, and then we get simultaneous equations reading across the top. 5 is equal to a plus b, and 2 is equal to minus 7a minus 11b. And so we can work out a and b, which actually didn't work out as particularly nice numbers. And so we now have the answer to our differential equation that we write it out again, but this time a was equal to 57 over 4 and b is equal to minus 37 over 4. And then that's the answer, except because this was a coupled question here right at the start, look, there is no y in this question. So when we, in a coupled differential equation, when we write the answer out, we don't write the y bit. The y was our construction. We just write the top line of it. So the actual answer to this question is this. Just the x bit with the correct a and b put in. And this tells us what the x value is doing for all times. So when time equals 0, we can put that in and we know where it starts. And then we can put time equals 1, 2, 3 in, and we could plot a diagram of this, which it asks you to do. And remember that x is this value here. It's just changing, that's all, and we'll get a lovely answer to it. Just quickly, the question then moved on to an entirely new question. Now, if you utterly failed part A and B, you still should have done part C, because part C is talking about the other spring. It's a new question, and it's entirely different. This time they tell us the eigenvalues are complex, and you should immediately know what's going on here. There's two things that are going on. One is you say, okay, is it complex, as in it's got a real bit and an imaginary bit, or is it just imaginary? If it's just imaginary, like plus or minus 7i, then it would be a center. In other words, the phase portrait is a bunch of circles or ovals. But this one isn't that. This is complex. So you know straight away it's a spiral. You look at only the real bit and say that's negative, therefore it is stable. Now, stable spiral is always based around the origin, and so we know that it is like a plug hole sinking into the origin. If you're sitting on a plug hole with all this spiraling water coming in to you, you'll never be able to move. You're not going to fall down the plug hole, you're just stuck where you are, because every direction you try and go, the flow will push you back. In other words, you're stable. So that's what the negative means. So I'm going to draw a negative spiral. And here's the answer on the mark scheme, but not many people that I marked got this. There's a few features that you must put in. First of all, there is a starting point. It's said in the question, it starts at 5, 2. So that must be a marked point, and there must be nothing to the left of it, before it. This is where it starts. We're dropping a cork into our flowing water. Where will it go? So you drop your cork in at the starting point, and then you must work out what direction it's traveling in at that point. Let's go back to the actual question. Here's the differential equation. It told us that A and B are 85 and 18 for this part. And so here's my differential equation. I know my starting point is 5, 2. So if I put that y coordinate in here, 2, then it's telling me the x direction, the speed in the x direction is a little bit to the right. Then I put in 5, 2 to the y direction. I get a very large number, so it's going down very quickly in that direction. Now overall, therefore, it's sort of going in this direction, slightly exaggerated because the y direction is far, far steeper than the x. But that doesn't matter, I'm just getting a fundamental direction. Now as soon as I've got that, that's my starting direction, then I can say it's definitely a spiral going in this, what is that, clockwise direction and heading towards the origin. Now they didn't join it up like that, because we actually don't know how many times it goes round before it hits the origin. So they didn't imply that. I don't think it'd be a disaster if you drew that. But they're just saying it's a spiral, that's the end.